Here is the plan for the day. I would like to briefly go through the Millikan experiment. The vast majority of you should know a lot of stuff that I'm talking about because you've done the research. So I'm just going to maybe go through, maybe it might give you a chance to maybe ask a question or go, oh, now I get it, or that kind of thing. I would not concern yourself too much with jotting these down. I would just sit back and listen if I were you. These will certainly be available online, but it certainly won't be any more in-depth than what you've already done or the 2 handouts that you've already got. Okay? Once that's complete, then I'd like to do a couple of sample questions with you. It will take probably the most of this period. Okay? Hopefully by the end of this period, we can come up with a day that the last day of filming can occur, or the last day of sort of project time will occur. I'm thinking sometime this week. I'm thinking Wednesday or Thursday. Maybe I'll just give you 2 options. You guys can vote. But think about that sort of in the back of your head while I'm talking about Millikan. So here we go. That is actually a slide of an actual Millikan experiment. Those are oil droplets in the background. This, of course, is a picture of Robert Millikan. So what was he trying to do? Well, most electric charges are measured in coulombs in a famous experiment known as the Millikan experiment because the guy was named Millikan. Discover the charge on one single electron. That's what he was trying to do. Find out how many coulombs of charge there was on a single teeny-weeny, tiny little electron. This charge is known as an elementary charge, which I've abbreviated to 1 E-L-C-H, elementary charge. He found one electron to have a charge of 1.6 times 10 to the minus 19 coulombs. Is that the number you found in your research, for the most part? Okay. You might have negative because it's on a electron and it's negative, but if that charge is on a proton, then it's positive. So really, neither here nor there, because it's known as the elementary charge, 1.6 times 10 to the minus 19 coulombs. What a wonderful Who Wants to Be a Millionaire question, right? If you ever have to phone a friend, remember that number. By the way, I am available if anyone's ever on Who Wants to Be a Millionaire. I am available to be phone a friend. However, if it's a question that you phone me and I deem that you should know it based on what I taught you, I will mock you on air.
Who Wants to Be a Millionaire is a game and we had to guess our answers and you can give us money.
I like the first part of that idea. Yeah? Guess what? Hannah's in charge of a review where we play Who Wants to Be a Millionaire. She's going to make up all the questions. Way to go, Hannah. Okay, so what he found was, now in the research that I've done, there's actually some differences that I've seen. One, I've seen that when he exposed the tiny oil droplets to X-rays, they became ionized. What does ionized mean? Gave them a charge, right? Ions have charge. They became ionized and thus charged. I've read in other books and stuff that just by coming through that plastic nozzle of the atomizer, which is really just a fancy word for spray bottle, yeah, the little bulb thingy, right? That they, just because of friction on the plastic, that they actually became ionized. I'm guessing the X-rays is probably more likely. So some of these oil droplets would have charges of -1, -2, or -3, or -14, or -27 elementary charges, right? And he thought that if he measured the total charge on a drop, it would be a small multiple of the fundamental or elementary charge. So if he could figure out what the lowest common denominator was, then that would be the elementary charge. Does that kind of make sense? Okay? It's not an easy thing to sort of describe. Okay? So he would have measured, he would have seen charges of -1, -2, -3, -17, Elches, and so on. But he would have seen them in coulombs, right? And so, like, for example, if the elementary charge was, say, 3.5 coulombs, and Peyton should be watching and listening, not texting. Oh. Sure, you've got the texting pose on. Okay. So if the elementary charge was 3.5, he would find some 3.5, some 7.5, some of 10.5, some of 14, some of 17.5, and he would know that if he could see those, what's the lowest common denominator? What's the one thing that goes into 3.5, 7.0, 10.5, 14, 17.5? It's 3.5. Based on that data, he would come up with the number, the elementary charge being 3.5. Now, it obviously isn't that easy. Right? I've obviously oversimplified. Because imagine he found charges of 1.6 times 10 to the minus 19. And then the next one, if it was 2 times, well, that would be? What's 2 times 1.6 times 10 to the minus 19? 3.2 times 10 to the minus 19. And another 1.6 would be 4.8 times 10 to the minus 19. And do you remember when we did the Finding Gravity Lab, how your data was all over the place? Do you think his is perfectly 1.6 and 3.2 and 4.8? No, it's going to be something like 4.75 times 10 to the minus 19 and 3.1 times 10 to the minus 19. It's going to be a nightmare to try and figure out what are these numbers all of. Remembering he did this in what was the year? What year was it? 1909? He certainly didn't have Excel that he could graph the results and find the trend line and line of best fit.
That was before TV, so they had to fill time somehow.
Fair enough. But he would have likely have graphed it, found the line of best fit, and determined sort of, what's that line of best fit and the slope. That's how he would actually have to do it. But again, with crazy, wacky numbers like this. This is what his apparatus looked like, right? You've probably seen this picture already, right? You got the top here, he sprays the oil into the top chamber, it falls through this hole here, and this is the area here where he would observe it. He had a microscope here, and he would watch the little oil droplets go falling down, right? He led quite an exciting life. They wouldn't make that sound effect, though. The top plate is positive. The bottom plate is negative. Remember, all these oil droplets all have a charge that is negative. So what does the top plate being positive and the bottom plate being negative do? It forces the charge up. Keeping in mind, there's also what force bringing it down? Gravity always brings you down. Electric forces are a little bit more uplifted. Okay. So Millikan sprayed oil onto the top of the top plate. Some of the oil fell through the hole. When the droplets were inside the two plates, they experienced two forces, gravity and the electric field force. And it looks kind of like that. Right, like I just drew. The force due to gravity can be calculated with Fw equals mg. So when the droplets are sprayed, they receive that negative charge due to the plastic nozzle or the X-rays. When inside the two plates, they experience an upward repulsive force. This force depended upon the strength of the electric field. Because if the electric field was turned off, what would happen? Well, it wouldn't be there. What if the electric field was on, but it was really big? Well, then the drops would start going up, wouldn't they? Right? So he had a little dial and he would turn up the electric field or turn down the electric field. He would hone in on one particular oil droplet that interested him, that seemed to be working good, and then he would adjust the electric field strength, eventually getting the drop to do what? Float, stay suspended. And that would be when the weight force was exactly equal to the electric force, right? And now, if he knew what the weight force was, because it's mass times gravity, he knows that gravity is 9.8. If he could come up with the mass of the oil droplet, he could come up with the weight force, and given that, that would give him the electric force, and knowing that it's QE, he knows the E, the electric field strength, because he's got it on his little dial thingy, and knowing the FE would eventually lead him to knowing the Q, which is in fact what he's trying to do. He's trying to figure out how much charge there is on that one little teeny weeny, itsy bitsy oil drop. And that charge is some multiple of the elementary charge that he had to eventually graph and find out. Not exactly something you can pull off in a half an hour. How long did it take him? Do you remember? 2 years? 4 years. Probably you're probably gonna see varying descriptions, right? It's fine. I'm not really too concerned about that. It's definitely a sort of a long-term experiment, right? So he noticed that the drops were slowing down, stopped, moving upward depending on the strength of the electric field, which he could control. And these behaviors seem to depend on the mass of the oil droplet, because the bigger the mass, the bigger the force of gravity, the charge on the oil, and the electric field strength. Now, this is where I'm going to lead you astray a little bit. Okay? He did not know the density of oil, and he certainly did not measure the drops of the oil droplets using a microscope. Okay? He used the viscosity of oil, which some of you have told me that there's some controversy around, right? He did much more complicated calculations to figure out the mass of our drop. To simulate that for you guys, to make it a bit of a challenge, to sort of put that step in there, but not to give you such a challenge that you can't do it, I'm going to substitute that with density of oil and volume and mass. Things that I know that grade 11 students can handle. Okay? So if you go on to university and you become a millikan expert, please don't come back and mock me. I'm doing this for a reason. Okay? I know it's wrong. That's what I'm saying. Okay, so he knew the density of oil, could measure the diameter of the drops using his microscope. He used this to determine their mass and then their weight in newtons. He could adjust the electric field force, cause their behavior to change. E was a measure of the charge in the drops. The greater the E, the greater the charge. Using this information, he calculates the drops' charges and found they were never less than a certain value. What is that certain value? 1.6 times 10 to the minus 19. They were never less than that. They were always greater than that number. That's the bottom value. That would be a charge of minus 1. And all of the charges were multiples of this minimum charge. They were always 1.6 or 3.2 or 4.8 or whatever the next one is, 6.4 and so on. Were they all perfect numbers like that? No, of course not. He concluded that the minimum charge was, that was kind of weird. He concluded that the minimum charge was 1.602 times 10 to the minus 19. Am I right, Brandy? Was that he came up with that number?
No.
His was a little different, right?
This was a little bit smaller.
Yeah.
It's like 1.59.
1.59, something like that? I think this is the modern accepted value, right?
Yeah.
Big deal, it was 100 years ago, right? We'll cut him some slack, yeah. I'll stop doing that now. What does the proton have a charge of? Positive 1.602 times 10 to the minus 19. What does that times 10 to the minus 19 mean? It means it's really 0.000000000, actually it's 18, right? And then the 1. Yeah. So, here's something that you might want to write down, because this is important. If one elementary charge is 1.602 times 10 to the minus 19 coulombs, how many electrons are required? How many Elches do you need to have a full 1 coulomb? Yes, you're going to answer it. All right, so what do you think? Is it going to be a really big number or a really small number? Should be large, Jake says? You know what? Of all the things that you learn in math, there are 2. In fact, I think I always say there's 3. I just can't remember what the third one is. But there are 2 things that you learn in math that people actually use in everyday kind of thing. Oh. Yeah, the 2 things in math that you absolutely positively do actually use in real life: percentages and ratio and proportion. You know what ratio and proportion are? Cross multiplying, all that stuff?
Yes.
Probably you learned it about grade 8, I'm guessing.
Yes.
Okay. 7 maybe? You actually do, people do these things.
It's been a long time.
Okay, so we're going to cross multiply here. 1 elementary charge is equal to 1.602 times 10 to the minus 19 coulombs. So X elementary charges is 1 coulomb. Notice that the tops are both in Elches and the bottoms are both in coulombs. Yes, you should write that down, and you should cross multiply. Okay, so does that cross multiplying make sense? 1 elementary charge is 1.602 times 10 to the minus 19. So X number of elementary charges is 1 Elch. You cross multiply.
So we're
It's this number times X. 1.602 times 10 to the minus 19 coulombs. X is equal to 1. Where does this 1 come from? 1 times 1. Divide both sides by 1.602 times 10 to the minus 19. And you get X equals 1 over that number, or 6.25 times 10 to the 18. Or in other words, 625, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, how many zeros? 16. 16 zeros, right? Because there's already the 2, 5 here, right? 1, 2, and then 16 more. In other words, many, many more than billions or trillions up in the Brazilians area. You've heard that joke? We would call 6.25 times 10 to the 18, we would call that the inverse of this number here.
This is where Millikan got in trouble.
This is where Millikan got in trouble by changing the numbers? Yeah. Let's see. Okay, so yes, it would require a whole lot of electrons to make 1 coulomb of charge. How come? Because one electron doesn't have very much charge on it. They're very tiny.
Animation?
If there's time, I'll show you the video.
30 minutes.
It's long.
That's good. No.
Let's go straight to these.
Okay, we're kind of...
So, here's example number 1. These are not scaffold, but they are sort of layered so that the first ones are easier and they get more and more difficult, more and more steps. A small ball of mass 6.5 times 10 to the minus 6 kilograms and a charge of 1.5 times 10 to the minus 10 coulombs is suspended in air above an electrically charged plate. Your job number 1 when you're doing a Millikan type question is look to see if the object is suspended or not. If it's suspended, what does that mean?
Okay. And the forces are equal.
It means the forces are equal. Exactly, Steve. Okay, that's a good thing. It's a lot harder when it's not suspended. Above an electrically charged plate. What field strength is required to suspend this particle in the air? So we are looking for the E, field strength. Okay, so I've got weight force and I've got electric force. What things do we know? I know the mass, I know the charge, and I also know gravity. Can I complete Fw equals mg?
Yeah.
Yes. So let's go 6.5 times 10 to the minus 6 times 9.8. Okay, so I get a value of 6.37 times 10 to the minus 5. That is newtons, right? That's how much force is going down. Because it's suspended, therefore, the electric force is equal to 6.37 times 10 to the minus 5, only in an upward direction. This technically is negative, that technically is down. The weight force and electric force must be balanced, and so the numbers are the same. Does that make sense?
For sure.
Peyton, does that make sense? Why not? Are you trying?
Yes, I'm getting there.
Oh, you just haven't got there yet. Okay. So Fw is equal to Fe. I'm asked to find what field strength. So what E? Now, E equals F over Q. My Fe, the electric force, is my 6.37 times 10 to the minus 5. The charge is given 1.5 times 10 to the minus 10. And yeah, you really need to be able to handle your calculator.
Is that E or F?
That's an E. So I get an electric field strength of 4.25 times 10 to the 5 newtons per coulomb.
And what's the E?
E stands for electric field strength. Fe is electric force. So really, that's only really 2 marks, right? Like there's that part and there's that part, right? E equals force over charge, right?
Yeah.
Any other questions?
Did I use my calculator in here?
I haven't seen a spare one lying around. Okay, so here's another one. I'm going to step up the degree of difficulty a little bit, I think. A small sphere of mass 7.0 times 10 to the minus 8 kilos is suspended in midair above a charged plate. At the point in the air, the electric field is 300 newtons per coulomb. What is the charge on the sphere? And I want the charge in Elches. I haven't said that, but I want it. So a little different question. But again, because it's suspended, the electric force is equal to the weight force. Right?
Yeah.
What's the first step?
Calculating Fe, maybe? Same thing with the performance.
Yeah, FW is equal to mass times gravity. I can't think of a physics question where if you're given the mass, you shouldn't go FW equals mg. It's almost always worth 1 mark.
Anytime there's something in math in there, you don't do that.
Yeah.
Sweet.
It's 7.0.
Yeah, just like that. It would be negative, yes.
Oh.
So you're going to get,
So why didn't we use negative? Did we use like negative for the last one?
yeah, we did.
Did you why?
And then I just said the electric force is equal to the positive value of that, that's all. Would I get too excited if you didn't do it here? Not really. It doesn't matter in the question whether it's negative or not. No, because really it's the number that matters, the value 6.27, it's not the direction of it that
So
matters.
we don't have to say that it's negative number 8?
It's not particularly needed in this case.
Okay.
Is it a good habit to get into? Absolutely.
So every time you do it, you start at negative?
You should.
Okay.
Gravity's
Sometimes, though, all I'm saying is that sometimes we're putting it in there, kids want to use it, and then it gets complicated again later, because suddenly the negative becomes positive. Okay, so anyways, I get 6.86 times 10 to the minus 7, and that is in newtons, correct? Therefore, yeah, the electric force is simply that same value, but positive. Right?
Wasn't it positive already? Oh no, it's negative.
This one is negative, so this one is positive. Now I'm given the E value here, I'm asked to find the charge. E equals F over Q. My E value is 300. My F is 6.86 times 10 to the minus 7. Solve for Q. Here's where all that solving equation stuff that you learn in math class is so important. Right?
Throw it in there.
That Q and the 300 are going to switch spots, aren't they, right?
Oh, for sure.
So Q is going to be 6.86 times 10 to the minus 7 over 300. And you get 2.29 times 10 to the minus 9 coulombs. 1 Elch is 1.6 times 10 to the minus 19. So how many Elches is 2.29 times 10 to the minus 9? Cross multiply. 1.6 times 10 to the minus 19x is equal to 2.29 times 10 to the minus 9. And basically all you're really doing is you're taking that 2.29 number and you're really just doing what? Dividing by 1.6 times 10 to the minus 19. That's what you're doing.
So where did you get that last number, that 1.6? Is
That is the millikan number. That's the number.
And you're timing it by x, and then where's it's supposed it equals that. But you just divide correctly right after that.
You can just, could you just take this number and divide by 1.6 times 10 to the minus 19? Absolutely. You go right ahead and do that. Just don't on the test say to me, Mr. Bennett, do I divide by or do I multiply by 1.6 times 10 to the minus 19? Because I'll tell you, well, you should cross multiply. Because if you cross multiply, you will always get it right. If you know how to do these, okay, you will always get it right. Because if you're going from Elches to coulombs, then you have to multiply by 1.6 times 10 to the minus 19. And kids always get them mixed up, and they want to just memorize what do I do, and then they get to the test and then they don't know, and then they ask me, and what do I say? Cross multiply. So if you want to just divide by and you can do that, great. Just don't expect me to help you when it comes to the test, because I expect you to be able to do it. Peyton has a question. Not really.
Because I was going to say, if it is important, it should have what they would calculate.
Is the 1.43 times 10 to the 10 important? Oh yeah, it's important. It's known as the elementary charge. It's probably like, that's a good question. I don't know. Yes, I'm guessing there are probably special chemistry calculators that have that built in, but you're absolutely right. To a chemist, that number is pretty vital. Yeah. Okay, so that would be a 3-mark question. Let's do the Big Daddy one. Okay? Big Daddy. Okay. Here's where I'm going to simulate the degree of difficulty by putting that density and volume thing in. Again, legal disclaimer, I know that Millikan didn't do this. It's just there to sort of expand the question, make it a little bit more challenging for you, give you an appreciation of the steps required. Okay, so an oil droplet of radius 0.0006 centimeters is located in a Millikan apparatus. It is suspended in midair above a 0.3 Newton per Coulomb electric field, and the density of oil is 800 kilograms per cubic meter. Determine the charge of the droplet in coulombs. Is the number 800 important? It is vital. The density of oil that we're going to be using is always 800. When you say to me on the test, Mr. Bennett, what's the density of oil? I'll say, remember that number from that test, that class that one day? That's the number. 800. Put that number 800 down on your cheat sheet. You need it. It is a constant. The density of oil is 800, and it shall never change.
Wasn't this going to be included in the question usually anyways?
I expect you to know it.
Is it supposed to be 800, like?
It's kilograms per cubic meter. If you have a cubic meter of oil, a big cardboard box full of oil, it would weigh 800 kilograms.
Does that break down to 800 grams per centimeter?
That's an excellent question.
Why do you have to confuse us, Jake?
The answer is no. How many cubic centimeters in a cubic meter, Jake? A cubic meter. Oh, I'm so glad he asked. A cubic meter is 100 by 100 by 100, which would be 100 to, it would be 1 million, yes, not $1 million, 1 million, 1 million cubic centimeters in a cubic meter. Hard to believe, right? You think about a sugar cube being about a centimeter. If you needed a cubic meter of sugar, you would need 1 million sugar cubes.
That's a lot.
I'll have to use that in the future. I'll call that the Pazlowski joke.
Okay.
Actually, I think I have to call that the Hannah Pazlowski joke, because if I'm not mistaken, there is a Joel Pazlowski one somewhere. What is the Joel Pazlowski line? I have it in my notes somewhere. I have a line that I have to say, and yes, Joel, he said something really funny one day, and I put his name to it. Can't remember what it was, though. So, because how many grams in a kilogram? 1,000, but there's 1 million, right? So it doesn't work. Doesn't work.
You mean the right answer?
No.
That, no. Jake was just wondering. Okay, how do we do this? Did alarm bells go off in your head when you saw that the radius was 0.006 centimeters?
No.
They should have. It must be in meters. Must be in meters. Why? Because this is in meters. Again, I'm just adding steps because this is the complexity that Millikan had to do. Okay, does anyone, first of all, we need to change 0.0006 centimeters into meters. How do you change it to meters? You do not times it. You multiply it because the number has to get smaller, right? Like 200 centimeters would be 2 meters, would it not?
Yeah.
200 centimeters is 2 meters, right? So you have to divide by, or in other words, move the decimal point 2 places to the left. So I'm going to have 0.000006.
Would there be an actual thing that you multiply by or divide by or no?
100.
Right.
The number, right? 100. Now, does anyone happen to know how to determine the volume of a sphere? Does anyone?
Pi. It's like pi r squared times height or something like that.
Very, very close. Pi r squared times the height would be a cylinder.
What are we trying to figure out? Pi r
We're
squared
trying to
times
find-
height divided by 2?
No?
Radius.
Is it like 4/3 pi times the radius squared?
Almost there. Volume of a sphere is 4/3 times pi r cubed.
That's important.
That's important.
Ah,
Volume of a sphere is 4/3 times pi times the radius cubed. Why did I say radius with emphasis?
We have right
Because every once in a while I like to be a jerk and I give you in the question the diameter
divided by 2.
divided by 2. Oh, Mr. Bennett, you're such a mean man. It is kind of jerkish, I agree.
yeah.
Did you know that I told you that, right? The jerk factor is the derivative of acceleration? Told you that, right? Yeah, like it goes like displacement, and then the derivative of displacement is velocity, and then the derivative of velocity is acceleration, and the derivative of acceleration of the slope of an acceleration curve is the jerk factor.
We should it there. Okay.
I'm not kidding anything there. He's being serious.
I think there should be another TV show about nerds, and it should be called The Jerk Factor. And then they have all these little acceleration jokes in there that only the nerds would get. Hey, what do you think? I've pitched it to CBS. They haven't got back to me yet. Yeah. Okay. So probably didn't get the joke. Yeah, right. 4/3 times pi. Let's just leave the letter pi in there. The radius is this number here. So 0.000006, and it must be cubed. Your calculator skills are important here. I'm going to pause and let you try to figure that number out. No, don't give me the answer yet? Okay. Well, I want to show you if you're right or not. Okay, if you want to know the answer, look up. If you don't, stay looking down. I won't say it out loud.
It is, spoiler alert, it is 9.
On your calculator, what order should you do it in? Well, it really doesn't matter. What you should do is go 4 divided by 3 times, and don't write down, because I know what 4 divided by 3 is, it's 1.3 repeating, right? Do not write down 1.3 and then punch that number back in your calculator. That's bad. Don't do that. Go 4 divided by 3 times pi. Use the pi button on your calculator if you can.
Oh.
Uh-huh.
I just hit to go to 4.
Use the pi button on your calculator if you can. 4 divided by 3 times pi times 0.000006 cubed, and then you must hit equals, because if you don't hit equals, the number on your calculator is only going to show you this 0.0006 cubed.
Are you the teacher that prefers the pi button on the 3.1?
I prefer the pi button.
Okay, because other teachers, they make us use 3.1.
Really?
Because not everyone has the pi button.
Oh, fair enough.
Screws up all
You know what? I really don't care. If you show me your work and you get some number close to that, I'm good with that. Yes. 9.05 times 10 to the minus 16. That's the volume. Okay, now what I really need to know, because what these other questions gave me was the mass. Do I have the mass? No. How do I get mass? I'm going to use this old formula, D equals M over V. And you know what? I really didn't even know if they teach this in science anywhere, do they?
I never heard.
Have you seen it anywhere?
No.
It used to be in grade 8. Okay, so density is mass over volume. No. The density of oil is the constant 800. We're solving for mass, and I don't know why it suddenly become a large M. The volume is 9.05 times 10 to the minus 16. So basically, you just multiply by 800, and you should get 7.24 times 10 to the minus 13 kilograms. All right, so Steve just asked a really good question. He said, now that we have the mass, now are we at the stage that we were in the first 2 examples? And the answer to that is yes, we are. You've now gotten to the point where you've got the mass to determine the charge in the droplet in coulombs. If you want to do that, now we go to this type of thing, electric force, weight force. So your next step now is to find the weight force, right? Mass times gravity, so my mass is 7.24 times 10 to the minus 13 times 9.8. Oh, I'll put my notes somewhere.
Is it negative?
Is it negative? It sure is.
No, I don't worry.
Sure is negative. Doesn't really matter.
No.
Not a great deal, but if you feel like you want to, go right ahead. So we're going to have negative 7.09 times 10 to the minus 12 newtons. Again, your math may be slightly off depending on some rounding errors or whether you're using the pi button or whatever. I don't care. Here's where I remember me harping at you at the start of the year about showing formulas and putting the steps in the right order. Do you think it's important now? Yes. Yes. Do not start your problem solution in the middle of the white space because you're going to run out of space.
Order doesn't matter.
Order does matter here. Now that I have the weight force, yeah, we're not talking about vector addition. Now that I have the weight force, I can go E equals F over Q. The electric field strength is 0.3. Now, should this be minus 7.09? No, it's 7.09 times 10 to the minus 12 all over Q. And so really what you're just doing is dividing by 0.3. I get 2.36 times 10 to the minus 11 coulombs. As you can see, organizing your work is very important here. You will get lost if you don't.
You don't really need that. Okay.
Jason asked, do we have to do that cross multiplying thing? The answer is no. Why?
It doesn't ask for
It
that.
didn't ask for it in Elches, it asked for it in coulombs, so you can be thankful. But if you were to do it in Elches, what would you do?
Cross multiply.
Do the cross multiply thing,
Divide it by
or just divide by, whoops,
1.602.
yeah, divide by 1.6 times 10 to the minus 19. Alrighty.
Here's some time to work on the
So
mail
that
file.
should help you with the problems on the at the end of the video. Here are some millikan problems for you to practice with. I'll hand these out.
Time for you to work on your mail.